Expression for wave number and frequency of spectral lines. Now what is spectrum, spectral lines, wave number and frequency? Okay, this is a dispersive medium. This is a suitable glass chamber filled with hydrogen gas at very low pressure. Okay, two electrodes are taken. If suitable potential difference is applied, then the hydrogen gas starts glowing. It is not burning, it is glowing, and that light is made to pass through a slit. If this is a cardboard with narrow vertical slit, something like this. If this is my hand, then this is the slit. Okay, similarly a slit is used. Light from this hydrogen after passing through this slit is incident on the dispersive medium. After dispersion, we can find different colors. After dispersion means light emitted by hydrogen must be polychromatic. Polychromatic means many wavelengths, and all those wavelengths can be seen. So these are called components of this incident radiation. If this is a white screen, so on this screen we find few lines. Why we find few lines? Lines are due to this slit. If this is the slit, then if light passes through this slit, on the other side we should find bright line whose width is equal to width of this slit, isn't it? If I increase the width, then this brightness also increases. So this is the slit. Because of this slit we get lines. If this is made of say 400 nanometer, 450 nanometer, 500 nanometer, 560 nanometer, 600 or 610 nanometer, only these 5 wavelengths are there in this incident radiation, means we can find these 5 lines, 1, 2, 3, 4, 5, and these 5 lines corresponds to these 5 wavelengths, and these are called spectral lines. This is called spectrum. Spectrum is arrangement of something according to some parameter. So in this case, arrangement of light according to wavelength or frequency. So that spectrum is this spectrum, spectral lines. And then wave number. Wavelength is lambda. Length of a wave is wavelength, isn't it? Now let this length be 1 meter. This length is 1 meter. If these are the waves, or this is a wave, count the number of wavelengths here. This is one wave, second wave, third wavelength, fourth wavelength, 4.5. So 4.5 wavelengths are there in 1 meter. So 4.5 per meter. So this is called wave number. Wave number denoted by nu bar, and it is equal to 1 by lambda. So nu bar is 1 by lambda. So wave number. And you know frequency. Frequency is number of waves or cycles completed per second. Let me summarize. If hydrogen gas is suitably excited and made to pass through a slit and a dispersion medium or dispersive medium, we can find components or constituent colors. So these are called spectral lines, and this is the spectrum of hydrogen. If light emitted by hydrogen has 5 wavelengths, only 5 wave lines can be found. Okay. Wavelength means length of a wave. Wave number means number of waves in a meter. Number of wavelengths in a meter. So SI unit is per meter. So we have to find expression for wave number. Energy of an electron in nth orbit is En equal to minus mz square e to the power of 4 8 epsilon naught square n square h square. Or this energy is also equal to mz square e power 4 8 epsilon naught square h square into minus 1 by n square. So let me take minus n square outside. Okay. Let me write the terms, where m is mass of an electron, z is atomic number, E is charge of an electron, magnitude of charge of an electron, absolute permittivity of free space, Planck's constant, and n is integral value 1, 2, 3, 4, principal quantum number. Okay. Now, energy in first orbit equal to mz square e to the power of 4 8 epsilon naught square h square into minus 1 by n1 square. There is n square here, n1 corresponding to E1, and E2 equal to same thing, mz square e to the power of 4 8 epsilon naught square h square into minus 1 by n2 square. Let me use Bohr's postulate. When an electron takes transition from higher energy state E2 to lower energy state E1, then there is emission of radiation. When an electron takes transition from higher energy state to lower energy state, then the energy difference is emitted as radiation. Therefore, h nu equal to E2 minus E1. Sometimes we can also write this as h nu equal to En2 minus En1. Okay. We have expressions for E2 and E1. Substitute these two in this expression. E2 is this, minus m z square e power 4 8 epsilon naught square h square into minus 1 by n1 square. Now in these two, these are common factors. mz square e to the power of 4 8 epsilon naught square h square minus minus plus 1 by n1 square 1 by n1 square minus 1 by n2 square. Students, did you understand this step? Minus minus plus n1 square. Write this as the second term. Therefore, frequency is given by, there is h nu on the left hand side, retain frequency, send h to the other side. Eight epsilon naught square, h square into h is h cube into 1 by n1 square minus 1 by n2 square. This is the expression for frequency. Frequency of spectral line, frequency of radiation emitted. But frequency equal to c by lambda, where lambda is wavelength. Therefore, frequency, which is c by lambda, equal to, expression for frequency is m z square e to the power of 4 8 epsilon naught square h cube into 1 by n1 square minus 1 by n2 square equal to, I want 1 by lambda. 1 by lambda, send c to the other side. m z square e to the power of 4 by 8 epsilon naught square h cube. 8 epsilon naught square h cube, bring this c to the other side, c into 1 by n1 square minus 1 by n2 square equal to, this 1 by lambda is wave number, nu bar. Nu bar is wave number. Leaving this z square, collect all other terms and denote it by r, z square into 1 by n1 square minus 1 by n2 square, where this r is replaced for m e power 4 8 epsilon naught square h cube c. m e to the power of 4 by 8 epsilon naught square h cube c, called Rydberg's constant, and the value of r is approximately 1.097 into 10 power 7 per meter. Observe this equation. n1 into dimensionless, z square is dimensionless, nu bar is 1 by lambda, 1 by wavelength means per meter. If left hand side is per meter, right hand side r should be per meter. Okay, and this is the value of Rydberg's constant, and this is the expression for wave number. Now let us get an expression for frequency in terms of Rydberg's constant. Okay, wave number is rz square constant, 1 by n1 square minus 1 by n2 square, and then expression for frequency is m z square e to the power of 4 by 8 epsilon naught square h cube c, h cube, and expression for Rydberg constant is mz square m e to the power of 4 by 8 epsilon naught square h cube c. In Rydberg's constant there is speed of light. In frequency there is no speed of light. So let us multiply and divide this by c, okay, and collect these terms. Leaving z square and c, what we get is Rydberg's constant 8 e to the power of 4, sorry, m e to the power of 4, m e power 4, 8 epsilon naught square h cube c, same thing here. So it is Rydberg's constant z square into c. So let me write this here, and expression for frequency is r c z square into 1 by n1 square minus 1 by n2 square. So this is the expression for frequency in terms of Rydberg's constant. This is expression for wave number and this is expression for frequency. Energy level diagram and spectral lines. Energy of an electron is En equal to minus mz square e to the power of 4 by 8 epsilon naught square n square h square, isn't it? So this is the expression for energy. For hydrogen atom, if we calculate, then the same expression becomes En equal to minus 13.6 electron volt by n square. So retain this n square and negative sign. M is mass of an electron, Z for hydrogen atom 1, E charge of an electron, constant, constant, constant. Simplify, that value will be in joule, divide that by charge of electron, that time we get minus 13.6. So let us solve this under problems, okay. For time being, please trust me and use this equation. Energy of an electron in nth orbit is minus 13.6 eV by n square. Now let us find energy for different orbits. If n is 1, E1 equal to minus 13.6 by 1 square minus 13.6 eV. Second, if n2, E2 equal to minus 13.6 by 2 square. 2 square is 4. So this is minus 3.4 eV. If n is 3, E3 equal to minus 13.6 by 3 square. 3 square is 9, minus 1.51. Use calculator, or simply you can use calculator, or you can simplify like that. You'll get 1.51. If n equal to 4, E4 equal to minus 13.6 by 4 square minus 0.85 eV. If n equal to 5, E5 equal to minus 13.6 by 5 square 0.54 eV. If n equal to 6, E6 minus 13.6 by 6 square minus 0.38 eV. Okay, we want all these values, and using all these values we have to draw energy level diagram. Students, learn to draw energy level diagram. If n is infinity, observe, if n is infinity, very high value, then E infinity equal to 0, isn't it? So 0 to 13.6. Draw y axis which represents energy. So in this energy level diagram, let us keep this height approximately 13.6. Okay. Now, this level corresponds to minus 13.6, lower value. So n equal to 1, energy is E1 equal to minus 13.6 eV. Okay. From here till here is 13.6. Here till here height is approximately 13.6. Next 3.4. Here to here let us keep 3.4. Observe, 3.4 is less than half of this. What is half of 13.6? It's approximately 6 point something. This is much lesser. So half of this, much less than half of. So let me draw second level somewhere here. Okay. So this corresponds to second level. Next 1.51. 1.51 is less than half of this. Students, what is the half of 3.4? 1.7. This is 1.5. Less than half. Half, less than half. Let me draw somewhere here. Okay. Point 0.85 is greater than half of this. So half is somewhere here, greater than half of this. Observe, n equal to 1, n2, n3, n4. After n4, n5. 0.54, which is greater than half of this. Approximately half, greater than half of this. This is for 5. Next, sixth, 0.38. 0.38 is greater than half of this. Half, greater. So somewhere here. This is for 6. 1, 2, 3, 4, 5, 6, 0. 1, 2, 3, 4, 5, 6, and then this is 0. So this energy corresponds to 0. So this is n equal to infinity. E infinity, energy at infinite level is 0. Okay. Now this is n equal to 2. And energy of the second level is E2 equal to minus 3.4 eV. Now let me write little bit carefully. This is N3, N equal to 3, and energy of third state is minus 1.51. E3 equal to minus 1.51. E4 0.85. So this is E4. N equal to 4. E4 equal to minus 0.85. 0.85. Next E5. This level is E5. N5, which is 0.54. 0.E5 equal to 0.54. Now this level is 6. N equal to 6. Energy in the sixth level is minus 0.38. Minus 0.38. There are other values. 6 after 6, 7, 8, 9, 10, and this energy tend towards 0. So here energy levels are crowded. The crowded energy levels are represented by this shading. Okay. Energy levels are almost continuous. They are discrete, but still, since they are crowded, energy difference is very small. It appears to be continuous. Electron can be found here, or here, or here. But in an assembly of hydrogen atoms, if electron takes transition from higher energy state to lower energy state, this is possible, infinity to 0. This transition is also possible, isn't it? Five to 1. This is infinity to 1. Next is 4 to 0. Next is, this is 6 to 0, 6 to 0, 5 to 0. Next is 4 to 0. Three to 0. 2 to not 0, 1. This is from infinity to 1. 6 to 1, 5 to 1, 4 to 1, 3 to 1, 2 to 1. And there are other levels. Let me denote that by this dotted line. Okay. If electron takes transition from higher energy states to lowest state, ground state, then this bunch of radiation is called Lyman series. Next, electrons can take transition from higher energy state to 2. Instead of going down to 1, they can take transition to 2. Like this. 3 to 2, 4 to 2, 5 to 2, up to infinity to 2. So we are not writing after this. All those are represented by this dotted line. Okay. If electron takes transition from higher energy states to 2, then this bunch is called Bohr series. Next, higher energy states to third level. If electron takes transition from 4 to 3, 5 to 3, 6 to 3, ultimate infinity to 3, then this is called Bastion series. Bastion series. Next, higher energy states to 4, like this, 5 to 4, 6 to 4, extending up to infinity to 4, like this, Lyman, Bohr, Bastion, bracket, bracket series. Next, higher energy states to 5. 5 should be from 6, isn't it? 6 to 5, 7 to 5, 8 to 5, then infinity to 5. Then this series corresponds to fund series, P fund. So this is how you should draw energy level diagram. After little practice, you can draw this, but make sure that the energy levels are not equally spaced. Okay. Why they are not equally spaced? Why they are crowded at the top means that's because energy level varies as 1 by n square. 1 by n square. If n is infinity, then energy is 0. That is the last level. So this is energy level diagram. Now, how about Lyman series? This series is due to transition of electrons from N2, 2, 3, 4, etc. to N1 equal to 1. That is this series. And this series lies in ultraviolet. This is in UV region of electromagnetic spectrum. Similarly, let us write for all Bohr, Bastion, bracket, fund series. For all this, you have to keep changing this as well as the region. Bohr series. This series is due to transition of electrons from 3, 4, 5, etc. to 2, and this is in visible region. This series is due to transition of electrons from 4, 5, 6 to n1 equal to 3. This series is in IR region. IR region means energy is less, energy is less. IR region. This series is due to transition of electrons from N2, 5, 6, 7 higher energy states to N1 equal to 4. This is in for IR region. Fund, also P fund. this series is due to transition of electrons from N2 6 7 8 to N1 equal to 5. This is in far IR region of electromagnetic spectrum. Okay. So this question can be asked for 5 marks. You have to write energy level diagram, then in this you have to mention transition as well as in which region it falls, whether it is in UV, visible, IR, far IR, far IR. Okay.